No late submissions accepted. How much time is left? Time is over. Those who have not submitted, they are late now. So let's start with our today's discussion. Should we start now? Okay. So, we'll discuss the solutions of the quiz tomorrow because tomorrow you'll also get the marks and the solutions, right? So until now we have been discussing about confusion matrix, data representation. So now we are ready to do some learning or we're ready to build some models. So we have been discussing a model like this. Some input x, maybe a vector, and some output y, and the model is f. So we have been seeing how to represent x, how to represent y, and we saw how to do it in NumPy, how to do it in
just to switch off that and switch on, sir. So switch it off and hold for the 2 seconds and then switch on.
ऑफ थोड़ी देर रखना
हाँ then switch on.
चल गया
ये चल रहा है उसको switch off कर. Now turn.
at the end? Visible? Okay. So we have been discussing that how to prepare X. We discussed data normalization. We discussed about tensors, and then we also discussed how to represent Y. We discussed about one-hot encoding, etc. Fine. So now let us discuss about F, the actual model which learns. So we saw an example of flowers classification, and how we are given the width and height of a flower, and from that we want to classify which flower it is. We can do similar thing. Let's say if somebody tells me somebody tells me what is the time of the day it is, and I can predict what is the position of the sun, right? So basically my X is the time of the day in my watch, and Y is the position of the sun, right? So can I build a model which can do this for me? So it is not a classification problem, it is called a regression problem. So basically what I am trying to predict, I am not trying to find some classes, disease or no disease, this flower or that flower, but I am trying to predict a continuous value. What is the position of the sun, maybe in terms of the angle, or maybe what is the time, or what is the temperature, what is the velocity of the car, right? These are all continuous values which I am trying to predict. So this problem is called a regression problem. So we will today discuss about regression. So here Y continuous value. Y is continuous, not discrete. Earlier we had discrete classes, but now it is continuous value. Okay, so let us say this is my Y, this is my X. They are scalars. X is a scalar, Y is a scalar. So I know at this X, this is my Y. Somebody told me. At this X, this is my Y. At this X, this is my Y. At this X, maybe this is my Y. Right? I'm just given these 4 points. Now, somebody asks me, at this X, what will be your Y? So what will you do now? How will you predict the value of Y at this X? This is the problem. A very common problem, like let's say I tell you at morning 10 a.m. the sun is at this angle, then afternoon 3 p.m. sun is at this angle, evening 7 p.m. sun is at this angle. Now what will be the position of sun at 1 p.m.? Right? Or it could be predict what is the temperature today given it is given the date. This is, what is the date today? 14th of June? 15th of June. 14th June. Okay, 15th of June. So on 15th of June, 15th of June, what is the temperature? So given the date, can I predict the temperature? Right? This could be one regression problem because I know in December temperature will be in somewhere low. In summer, June, temperature will be somewhere here high. Okay, so given the date, can I predict the temperature? Or given the date and the humidity value and the position of the sun or how much cloudy it is, can you predict the temperature? Right? When our x is, now my x is multidimensional and I want to predict y, which is a scalar. So, okay, let us restrict ourselves to scalar x and scalar y. So, how would you solve this problem? Huh? Okay, so you try to fit a curve. Try to fit a curve to these points and try to find out the value. Okay, let me try to do it mathematically or pictorially. I will try to fit a curve. Right? And then I will say, okay, whatever is my x, this will be my value. Right? So let's try to do it mathematically. So I have my y, I have some x, some y. These are given to me. Let's say this is so when x is how much it is? 0.2. My y is, that's a 0.9 or something. When my x is 0.4, my y is 0.8 something. When my x is, let's say 0.6, my y is minus 0.6. When my x is, okay, let's say 1. Then my y is minus say 0.3, right? And I ask you when x is equal to 0.3, then y is equal to what? Right? So what I can try to do is, I can say, let us construct a y hat. Y hat is a function of x. Right? Such that this y hat satisfies this, but it also can be generalized to or interpolated to other values of x. How many of you saw the video dealing with data? How many of you saw the video dealing with data? Did you see something like this there? Did you see something like this there in that video? Okay, yes, so we saw something like this. So I'm just elaborating those points with different examples now. So, okay, a simplest way to choose f is a linear model. I can say my y is some w0 plus w1x plus w2 x square plus so on. How many of you think if I take a very large value, which I keep on going to a very large degree of x, I will be able to exactly find the curve? Means I can fit any f of x using this. How many of you think I can never fit f of x? So there is a theorem called there is a theorem which says you can if you take a general function of this form, basically w0 plus w1 x to the power 1, w2 x to the power 2 plus so on, plus wd x to the power d. If your d is sufficiently large, you can approximate any function fx. Any function fx. Which theorem is that? Huh? In mathematics, you might have read this theorem. It's called least square theorem. It's called Taylor's theorem. How many of you have heard about Taylor's theorem? Everybody has heard about Taylor's theorem now. Okay, so it's called Taylor's theorem. Okay, so taking some idea from Taylor's theorem, what we are trying to do is, I don't have derivatives here, right? So I cannot exactly use Taylor's theorem, but I can take a general function like this and try to estimate the values of w which will fit any function. Okay? Here in this case the function is unknown to me, so I can find some w's which can approximate this as best as possible. So so how can I do that? So basically I want to, what is my objective? So machine learning, the most essential principle is to define your objective function which you want to optimize. It's called objective function or loss function or error function, whatever name you want to give. Let us call it as an error function for the time being. Error function. What I want to do, I'm saying if my y is ys, means the first sample or second sample, I have 4 samples, right? So ys are those samples, minus my fx. Right? Whole square. I want to minimize this for all the s. This is my error function which I want to optimize. So can I write it like this? Okay, let's go to the previous thing. So here this thing can also be written as summation I equal to 0 to capital D, or let's say capital small d, goes to wd x to the power d. Can I write like this? Means this is just summation, this is shorthand representation. Okay, so let me put it here. Can I write like this? Right? Now I want to minimize this by means what is, how do I change? Ys is fixed, right? It is given to me. Xs are also fixed. Like look at this one. So my ys and xs are fixed. But what is changing in my equation here? It's the wd by changing or by estimating wd. So there, how many such parameters are there? D plus 1 parameters are there, right? D is equal to 0 to capital D. Correct? I want to minimize E subject to this. How do I do minimization now? How do you find the minimum of a function? Huh? Differentiate and equate it to 0. Because at the minimum, my derivative is 0. Okay, let us say, let me draw a function. So, this is a function. So, this is my E. And this is my W. any W, it can be W0, W1, whatever. So I want to find the best W, which is this one. So how do I find it? I know that the slope will be 0. Right? That's what I am going to do now. So I am going to differentiate E with respect to a W and equate it to 0. Let's do it with respect to a general W, let's say, okay, W, let's say dE upon D. Let me call it as partial derivative because I have so many W's, I take one of them. Let me call it as, what should I call it as? D is, okay, Wi. This will be equal to summation over S. So the derivative of this thing is twice of sorry. Just a minute. Okay, so what is the derivative now? 2 ys minus summation over d w dx s to the power d into correct? Where I can be between 0 to, I can be any, I belong. I can be one of these, any of these values. Now I have to equate it to, so this thing will be equal to 0. Right? Then what do I get? This becomes, so 2 goes away, this becomes summation over x ys minus, okay, let me try to open it now. Right? So what do I get? Just a moment. Okay, so let me just write it here. So I got 5s. What was it? ys xsi is equal to summation over S, summation over D. Right? Correct? So can I now, okay, let me try to write it in the matrix form now. This will be, let us say, so basically this is a linear equation. How many equations are there? I is equal to 0 to d minus 1, so I get d minus 1 I. So I get d plus 1 equations. Correct? And I can solve them. If I write them in the form of matrices, I get something like this. This becomes, if my A matrix is x s to the power d, here d goes from 0 to d and s goes from 0 to s. So this is a matrix like this. Means my A is x 0 power 0, x 0 power 1, 0 power 2, so on, and then x 1 power 0, x 1 power 1, x 1 power 2, so on and so on. This is my A. Then this becomes A. Okay, this thing. Okay, let me write I here and D here. And this thing becomes A times W. This is a vector, this is a matrix. This is A transpose. And this is A transpose times Y. So my W becomes A transpose A inverse A transpose Y. Right? Just for clarification, I can also write this. I can also write this as y hat is equal to. I can say my y hat is equal to A times W, right? So what I get here is this solution.